Thank you very much, Professor Liew, for that very interesting presentation. I open the floor now for the question and answer session. The gentleman at the back there.
Hi, my name is Payman. I'm Principal Structural Design Director with the Ted Jacob. I have a number of questions, but I know I have just limited time. My first question is for Mr. Yi Fu regarding his structural for the hexagon steel structure. So, because I've done so many research for the hexagon, steel structures, my question is regarding your tower. What was your optimum angle for the hexagons? Because I've heard you, I don't know if maybe I'm mistaken, so you talk about 19 degree. That was the optimum angles for the hexagons, or did you do any FEM analysis to come up with that optimum angles?
From the curve, we studied from 30 to 5. Finally, we find that 19 is the better, is the best one. But we only changed the 4 corners columns, because 4 corner columns mainly is for the overturning moment.
Yeah.
Mainly is for the vertical. But for the Weber and the French, the mid area, we not change the angle for the shear deformation and the shear stiffness.
Okay.
That's okay?
Yeah, thank you so much.
Thank you.
Can I ask another question, or?
Sure.
Sorry. It's my second question is to Mr. Sun Moon. Obviously, you were talking about the diagonal system for tall buildings, and you compare the ratio of height as long we go up for the super tall building, the angle will change. So what is your recommendation? Shall we keep the angle as long we go up to the super tall buildings and just play with the aspect ratio of the height, or we have to change the angles as long we go up to the upper level in the tower?
I mean, the tall building design should be integrative approach between architects and engineers and other people. So, I mean, my study just shows what's from structure's viewpoint, what's the best scenario. I mean, using the least amount of material, just getting the same results. So, in terms of structural performance, just in terms of diagonal structures, it's better to use the steeper angle ranging somewhere about 80 degrees at the bottom, and then about 60 degrees at the top.
Okay.
That's for the structural purposes. But if architect's intention is different from that, then it can be deviate. But I wanted to discuss this is a structural implication, and then what I mean the.
Yeah, of course, because we obviously structural engineers, and we look at the structural performance first, then the architectural. That was my question, to what the optimum, for the lower and the upper part. Thank you so much.
The gentleman over here. We'll have probably two or 3 minutes left.
Thank you. Phil Gardner of Irwin Consult in Melbourne, Australia. Just again a question for Mr. Yi Fu, if I can. With the hexagonal grid tube and the extra deformation from axial load, did that mean you had to delay the facade cladding because you had to get more building load on before you could attach the facade?
The facade is just in the hall, the edge like that. The facade is after the main structure finish, then start to the facade. Yes. Okay.
We'll have just 2 more questions left. Gentleman over there, and then one over here.
J.C. Gerardi from ArcelorMittal. I have a question to Professor Liew. He's referring to the different codes. And if you take, for example, the Euro codes, they are limiting the grade of the concrete to 60 for composite design and for 60 in the steel. So American codes also are limiting the yield, ACI also limiting the grade. So how could he use high-strength steel, extrapolating some formulas from standard codes and predict all this behavior. So I guess in the Singaporean codes, the S700 is not included also.
Okay, since you mentioned about Singapore, we're allowed to use a concrete strength up to 105 for reinforced concrete design. For steel, you can up to, well, if you go beyond 460, it's very difficult to get it because Singapore, you import everything, including water, stones, sands, everything. You are right. The current code of practice, especially the modern code of practice, do have limitations on the strength of steels to be used and also on the concrete strength. That's why research is needed, because there's inventions from the supplier coming with a higher strength material. How are they going to use it in the constructions? So we have performed some tests, and the test verifications as compared whether how we can extend the current code limitations and to predict the strength. So we've done tests, we've also done fire tests on that. And we're going to come up with the design recommendations for that.
I have a question about the second presentation. So you compare the wind-induced deformation for different shape of building. But wind load is shape-dependent loading. So if you change the shape or twisting angle added, the wind load can be different. And especially in the high-rise building, crosswind response is very significant. So in that case, in the case of straight square prism, the well-correlated vortex shedding induced a very high crosswind response. But in the case of twisting model, it can be reduced significantly. In your study, you didn't mention about how treated the wind loading. So could you expand about your assumption of wind loading?
My study currently presented is the wind load is based upon ASC defined code loading, and then we met before, and then I'm kind of studying your study about the wind effect of various different forms like twisted, and then that's kind of my next agenda. So my presentation is kind of fundamentally based upon the code defined load at this point.